All right, I'm back. We're on page 306, and we are going to answer two really common types of calculus questions. So once you know what a derivative is, right, it's the slope of a curve at a point, slope of the tangent line, instantaneous rate of change. It could be velocity of the function's position. I guess you get the sense that there's like a lot of applications of derivatives. Once you know what a derivative is, you start being able to answer weirder questions, right? Where's a function increasing? Where's it decreasing? Where does it have a maximum, a minimum? Let's look at this question, which is like none of those. Find all values of x at which the tangent line to the given curve is perpendicular, right? So perpendicular means at right angles to the line y equals x. For the curve, y equals x plus 3 over x plus 2. Sketch the whole scenario and graph it on your calculator. Okay, so what's going on? All right, so I need to be perpendicular to y equals x. So y equals x has a slope of 1. So the slope of the perpendicular will be the opposite reciprocal. So therefore, the slope of the perpendicular is -1, right? It's really -1 over 1, but like -1. And so I'm looking for where the slope of the curve, the slope of the tangent line, but the slope of the tangent line is the same as the slope of the curve. I'm looking for where the derivative of this function is equal. I really hate the way that when you go over, I mean, it makes sense because if you do it in the real world, it gets darker as you like whatever. But I wish it wouldn't do that. I wish it would like perfectly know like not to get darker when you do it. Anyway, we're looking for where the derivative of that thing is equal to -1. So I'm gonna have to find the derivative. So let's dive in and see if we can do that. So it's a quotient, so I'm gonna use quotient rule. So dy dx is the bottom, the derivative of the top minus the top derivative of the bottom all over the bottom squared. Okay, so if we simplify this, I get x plus 2 minus x minus 3, so I get -1 over x plus 2 squared. Okay, so there's actually a thing you could have done here. So you could have rewritten x plus 3 over x plus 2 as, so I'm going to take, this is weird. So typically I call this the +1 -1 trick, which like doesn't really make sense in this case, but I'm going to break 3, I'm going to partition 3 into +2 + 1 over x plus 2. And then I can make that x plus 2 over x plus 2, and then +1 over x plus 2. So I could rewrite y. You could also do long division, which would give the exact same result. But I get this. So this is going to be helpful because I'm going to actually sketch the graph. And this graph is easier to graph than the original. But also this derivative is a little easier to take because the derivative of 1 is 0. And then if you use a quotient rule on the second part, the derivative of the top is 0. So like a lot of stuff just zeroes out. And you end up here no matter how you do it. So we get this, and then I need these two things. So I need this and this to be equal, right? So I'm going to set them equal. So I get -1 over x plus 2 squared equals -1, which means that x plus 2 squared is equal to +1. Okay, so how can I go about solving this? Like two ways. Well, actually, there's just really, well, there's two ways. I could subtract 1 from both sides, and then I could do a difference of squares, and like that's weird. I could take square root of both sides, get x plus 2 equals ±1. So x equals -2 ±1. So x is -2 plus 1 is -1. -2 minus 1 is -3. Same answers either way. It doesn't really matter how you do it. So I get -1 and -3. Like, does that feel right? So the function has a vertical asymptote at -2. So it kind of feels like maybe that's the right thing. So I'm thinking that these are my answers. So I think that's my answer. Let's graph and see if it makes even a little bit of sense. So If I were to graph, so I'm graphing this version because it's just like, I should use color more, as previously mentioned. I'm gonna graph this because it's a little easier to graph. So got this. Okay, at -2, there's a vertical asymptote. So here, and then there's a horizontal asymptote at y=1. So think about limits at infinity, or think about 1 over x, and you're shifting it up 1 and 2 to the left, which is actually probably the better way to think about it. And our curve be like this, and like this. Ugh, not great, but you know, you get in a sense. And then y=x is, let me use something. So y=x is like this. Okay, and what I have found is I found that at x equals -1 and -3. So -1 is maybe like here. And if I put a tangent line, that feels like it could be right. And then at -3, I would put, I don't really know. This one's not as good, but you know, oh my God, what? Yeah, I mean, why not? You know? So I feel like these are totally plausible answers based on the graph. Knowing how to graph these things is like a huge advantage when you're doing these sorts of problems. So what I want to do now is I'm going to use the calculator. So I think x equals -1, x equals -3. I think those are my answers. I think that the graph supports that. I'm going to use the calculator to like solve the entire problem and see if the calculator agrees. So I'm going to do a whole new document here. All right, f of x is going to be x plus 3 over x plus 2. All right, so what did we do? We solved, so menu 3, solve derivative with respect to x of f of x equals -1. So you need to know that part, right? You need to know that perpendiculars have opposite reciprocal slopes. The slope of y=x is 1, so the slope of the perpendicular is -1. Solve this for x. We get this, -3, -1. All right, so does that make sense? Let's look at the graph. I mean, yeah, we already know it does, but you know, check it out. So f of x, good. I'm gonna add y=x. Okay. Now tangent lines at negative. So let's do a really weird thing. So the tangent line at x equals -3, for example, will be f of -3 plus the derivative at -3, but we already know that it has to be -1, times x plus 3. Okay, that looks pretty good. And then let's do the same thing at -1. So f of -1 plus the slope at -1. So what I'm doing is I'm taking point slope form, y minus y0 equals m x minus x0, and I'm moving y0 to the other side so that I can graph it on the calculator. That's a really common thing to do. X plus 1, we get this. Looks perfect. And that looks a lot like our graph, right? So I don't have the vertical asymptote in. I never put those in. You could if you wanted to. In graph entry edit, one of the options, equation templates. One of the options is line. You can put a vertical line at -2. That doesn't look great. So if you control menu while above it, you can do something to this. I'd like to change the way this looks. I don't even know if that's possible, actually. I want you to be a dotted line. Please edit relation? No. How about this? What is this? History? There's got to be a way to make that dotted. I don't know what it is, though. Attributes. Line weight. Here we go. Dashed. Perfect-ish. I should have changed the color while I was there, but I didn't. All right, so I think we got that problem done. We had to think about slopes, and we had to think about perpendicular slopes, taking derivative, using the quotient rule successfully. But we solved it using things that we know, and that's the name of the game. We want to just keep taking things that we already know, getting better at them, and using it for more stuff. So I'll be back in the next video to finish this page, and we're going to keep going. So see you then.